Okay, welcome back. And today we're going to look at the more about the executor, and we'll take another look at the scanner. Okay. All right, so let me go ahead and share my screen. All right, put this away, and you should be able to see my screen now. Okay. All right. Any questions about assignment number 3? Okay, this is a fairly involved assignment. You are finishing the parser by adding these statements: a while statement, if, for, in case, and then you're also adding visit functions to the executor in order to execute those statements when you visit the nodes of your if tree and your while tree and so forth. Okay, so if there are any questions about this, let me know. Use the discussion feature. Don't wait until the last minute to work on this, because you're going to run into a number of issues that you'll need time to fix. Okay. And again, you can start by with your solution to assignment number 2. Okay, or you can start with my solution to assignment number 2, and I have posted my solution. So either way, you're going to be adding new parser, parse functions, and you're going to be adding new visit functions. Okay. All right, and then I supplied the test files for you to parse and execute. Okay. All right, that was assignment 3, and you have until I believe a week from Thursday. Okay. Now I did make in my solution to assignment number 2, I did make an improvement over the simple CPP that I gave you, and let's take a look at what that was and see if we can figure out how it was possible for me to make that improvement. Okay, so let me move this out of the way here. All right, so if you look at the executor class, right, this is in simple CPP, which is what I gave you to start when you were doing assignment number 2. You'll see that the constructor for the executor, I passed in pointed to the symbol table, right? Remember, the hack that we're currently using is that when we're executing the program, we are storing the current runtime values of each variable in the variable's symbol table entry. Okay, and I told you that was a hack. Okay, we're going to have to get away from that later. Okay, but in order to allow that to happen, of course, then the back end needed access to the symbol table, which is why we passed it in to the executor. Okay, now in my solution to assignment number 2, you'll see that the executor does not get a pointer to the symbol table, okay? And yet, we're still using the hack of storing the runtime values of the variables in their symbol table entries, okay? So the question is, how is the backend executor able to do that if it's not passed a pointer to the symbol table? Okay. Remember, it's the parser that creates the symbol table, and as it's parsing the statements, you know, it's putting entries into the symbol table. Okay, so then the backend will need access to the symbol table. Okay, and our hack says that we're putting runtime values in the symbol table. Okay, so does anybody know how we managed not to pass the pointer to the symbol table. Okay, so how does the executor then work this hack? Anybody have an idea? Okay. Okay, let me give you a clue. Okay, when we build the parse tree, or when the parser builds a parse tree, and it's creating a variable node, okay, yeah, to put, it creates a variable node to put into the parse tree. For example, the parse tree for an assignment statement, the first child is the variable node that represents the left-hand side, the target variable of the assignment, okay? What is in that variable node? Let's take a look. There's node.h, okay? Look at this. Okay. So in the parse tree, whenever there's, for every variable node, okay, each variable node contains a pointer to the symbol table entry of the variable, okay? So if we look at executor, okay, of my solution to assignment number 2, here is assignment, and LHS for left-hand side is the node that represents the left-hand side variable. And you can see here, we are now accessing the pointer to the symbol table entry, okay? And therefore, we can set its runtime value into that entry, okay? So again, we have, as one of the fields of the tree node is the pointer to the symbol table entry, okay? And we use this field if it's a variable node, okay? All right, and you can see that the entry also has a value, okay, which is what's going on here is that once we get a pointer to the entry, okay, from the node, okay, well, actually, the value that we're setting is in the symbol table entry, okay, that is, okay, here's the symbol table entry, and there's the value. That's the value that we're setting into the symbol table entry. Okay, so that was what we saw here. Okay, is this set value. Okay. All right, so that was a simplification. Now that also means that any lookups of symbol table entries has already been done by the parser, because it's gone ahead and looked up the entries in the symbol table, okay, and put the pointer to that entry in the tree node, okay, and therefore the back end does not have to do any symbol table searching, because that was already done for it by the front end parser, okay. So, so there's a definite division of labor here. You know, if the parser can do a lot of the work ahead of time, then the executor can execute the program that much faster if it doesn't have to spend time doing symbol table lookups and so forth. Okay. All right, so I wanted to point that out. Okay. Okay. Don't know if anybody noticed that I had put in that small improvement. Okay. Okay, let's bring up here. Okay, we had some. I showed you how the scanner works. Remember, it skipped over leaving blanks, and then the first non-blank character told the scanner what the next token was going to be. And at any point in the source file, okay, as it's moving along, it tries to extract the longest possible token. So for instance, okay, let's say that the current character that the scanner sees is the less than sign, okay? It doesn't immediately say, oh, the next token is the less than token. it tries to extract the longest possible token. And if the following character is an equal sign, then it's going to extract the less than sign and the equal sign, and that the two of them, those two characters will then constitute the less than or equal to token. Okay, so scanner is always trying to extract the longest possible token. So it keeps reading characters until it comes to a character that cannot possibly belong to the token that is currently building. Okay? So there's a funny term for this. It's called maximum munch. Okay, that means the scanner is consuming as many characters as it can, and in order to construct the longest possible token. Okay, so remember maximum munch. Okay, because we're going to see that term again. Okay, all right. Well, here it is, the parser. Okay. Remember the parser, it knows the grammar of the language. So it tries to parse the longest possible statement. Okay, so when it's parsing a statement, it tries to parse the longest possible statement. And again, that's maximum munch. Okay, so we saw that, okay, when we were talking about the dangling else. Okay, so here the parser got an if, and it got the expression, it got the reserved word then. Remember, the parser is getting these tokens from the scanner. Okay, and then it sees the reserved word if. Okay, now remember I said that this else belongs to this then. Therefore, this is an entire if statement. Okay, so using the maximum munch principle, okay, the parser, okay, it knows it's parsing an if statement, it's parsed the expression, it parsed the then, it sees an if, okay? So then it's going to start parsing this nested if, okay? And it's going to try to parse the longest possible statement, which would be everything that I have in yellow here, okay? So it's not going to stop after the 500 and say, oh, it's not going to say, I'm going to stop here and say that this if-then statement belongs to the then, and then this else belongs to the outer if. Okay, it doesn't do that, because once it starts parsing this nested if, it's going to go all the way. Okay, it's going to try to parse the longest possible statement, and again, that is maximum munch. Okay, so maximum munch occurs with the scanner when it tries always to parse or scan and return the longest possible token, and maximum munch occurs with the parser. When it starts parsing a statement, it's going to try for the longest possible statement. Okay? So there you go, maximum munch. Okay, we've been talking about syntax, right? Syntax refers to the grammar rules. Okay, it says, okay, if you have a statement, this is the proper way to write a statement. Okay, so we have the proper way to write an if statement, proper way to write an if then else statement. Okay, those are the syntax rules of the language. Okay. And it's the parser. It knows the grammar, and then we describe the grammar using syntax diagrams. Okay, that's syntax rules. Okay, so therefore the parser can do syntax checking. When it's parsing a statement and it runs into a token or whatever that doesn't belong to that statement. Okay, let's say that it's parsing an if statement, and after it's parsed the Boolean expression, it's expecting the reserved word then. And if that word isn't there, then obviously that is a syntax error, and the parser would know that. Okay, because remember, we use syntax diagrams to describe each grammar rule, and then we write the parser to match the syntax diagram. So our parse if statement function, it will follow what the syntax diagram for the if statement says. Okay, so it's going to, after it's seen the reserved word if, it's going to expect to parse that Boolean expression. After it's done parsing the Boolean expression, it's going to expect to see the reserved word then. Okay, so if none of these occur properly, then we have a syntax error, and the parser is going to know that. And presumably, then it writes out some sort of error message saying that, hey, this statement is invalid. Okay. All right. So syntax checking is an important function of what the parser is doing. Okay. All right. Now, there's another concept called semantics. Okay. Semantics refers to the meaning of a syntactically correct statement. Okay, so first of all, you need to make sure that the if statement is syntactically correct. Okay, then what does the if statement mean? Okay, well, it means that now you have to evaluate, at one time, you have to evaluate the Boolean expression, and if it's true, you do the then statement. If it's false, you do the else statement. Okay, that is semantics. Okay, so that's the semantic rule of an if statement, which is, what is its meaning? What are you supposed to do about this statement? Okay, so okay, the semantics then obviously determines if you're writing an interpreter, how are you supposed to execute this statement? Okay, if you're writing a compiler or a converter, how are you supposed to generate object code for that statement? Okay? So you need to, based on the meaning of the statement, either execute it correctly or generate correct code for it. Okay, that's semantics. And as we develop our compiler, we have to know that, okay, we're doing syntax checking, and now we're doing semantic checking. Okay, so those are going to be two separate operations that we're going to have to perform. Okay. Now, in the beginning, they're kind of conflated. You know, they're maybe the distinction isn't quite so clear, but later on, we definitely have to know which it is that we're doing. Okay. All right. So how does the parser deal with semantics? I just explained what the backend does. Well, the parser also has semantic actions, right? The parser has to know the meaning of an if statement in order to build the correct parse tree, right? It has to know that, okay, I need an if node, and the first child is going to be for the first child is going to be the root of the expression subtree, and then the second child is the root of the then statement, and third child is the root of the else statement. Okay, so that's a semantic action. The parser has to understand semantics in order to build the proper parse trees. Okay, and then building the symbol table. Okay, you know, the parser has to know that, oh, if there's a variable, then we have to do some symbol table operations. Either we're entering that variable name into the symbol table, or we're looking up the variable name. That's another semantic action. Okay? Later on, our parsers is going to have to do type checking. Okay, well, you know, if you're adding two things together, are they numbers? Okay, which is allowed. But if you're trying to add two strings together, well, the Pascal semantics doesn't allow that. Okay, so again, type checking is a semantic operation. Okay, you know, the operator precedence rules. That's another semantic action. You know, it has to know. Parser has to know that, okay, multiplication has higher precedence than addition. Okay, and so therefore it will build the proper parse tree, okay? So that the back end doesn't have to worry about things like operator precedence, because the parser's already made sure that the parse tree that it built has encoded the precedence rules. Okay? All right, so syntax and semantics. Well, syntax checking is definitely done by the parser in the front end. Okay, that's, you know, if the parser has found any syntax errors, it should not allow the backend to do any work, because then it can't guarantee that the parse tree is correct. Okay? Semantics is done by both the parser, as you just see here, and by the backend. You know, either when it's executing the program or it's generating object code. Okay, so semantics appears both in the front end and in the back end. And the fact that the parse tree was built properly and the symbol table was built properly is due to the parser in the front end knowing the semantics of the language. All right, as I said, the distinction between syntax checking and semantic checking will become clearer as we go along. Okay? All right, so I just explained all this already. Okay, now syntax error handling. Okay, so what should happen if there is a syntax error? You know, you misspell a reserved word, or you're missing a parenthesis or something. Okay, what should the parser do? Okay, well, syntax error handling is actually a three-step process. Okay, obviously, first of all, you have to detect the error. You know that, hey, there's something wrong here. Okay, then you flag it. Okay, flagging means, okay, you put out some sort of message that, you know, points out the error and hopefully explain what the error is. Okay, and then you have to recover from the error. Okay, what should the parser do after it has detected and flagged the error? Okay, so, but all three are important. Obviously, if you don't do number one, then you can't do any of the other things. Number two, you do want to point out the error. So maybe say line number such and such, maybe print out part of the statement around the error, or at least say what column you found the error in, and then a clear error message. Okay, and I know, and you know that the C++ compiler is notorious for putting out cryptic error messages. You know, you do something simple like, you know, leave off a semicolon or whatever, and you get these weird messages that you really wonder who wrote these messages. Okay, so you want to have clear messages. Okay, now recovering from the error, that is quite a challenge. Okay, and we'll talk about that in just a second. Okay, I want to say that good syntax error handling is a real hallmark of excellent compiler design, right? Because when people write programs, they're going to make lots of errors. Okay, it's just an artifact of being programmers that you're going to make a lot of syntax errors. Okay, so you want the compiler to do a good job of detecting the errors, putting out clear error messages, and then recovering from the errors. Okay. All right. So how does a parser recover? Okay. Maybe the parser just stops after their first error. Okay, so you know it's going through your program, and oh, you're missing a right parenthesis here. Okay, so it writes out a message, and then the whole thing stops. Okay, so you only get one error at a time. Okay, and that's easiest for the compiler writer because, hey, detect the error, flag it, and then exit. Okay, it's not so good for the programmer because if there are a number of errors in the source code, the poor programmer has to compile over and over again, and each time catch one error and then fix that error, compile again, catch another error, and so forth. Okay. Now, nowadays, the turnaround time is, so fast. You just press the compile button and off it goes. Okay. Now, back in the old days, when turnaround time was like a day, then every error cost you a whole day's of work. So stopping after the first error is not the best thing. Okay. Now, of course, the worst case is that your compiler just crashes. It detects an error and crashes, okay, or hangs. Okay. Now, another thing that could happen is your compiler just becomes hopelessly lost. Okay, you're missing. You have if then else statement, and for some reason you left off the reserved word then. Okay, and the parser is parsing along. It's in the middle of an if statement, and then it gets lost. Yeah, and it just goes crazy. It doesn't know where it is, doesn't know which rule to apply. The wrong parse functions get called, and you get reams and reams of error messages. Okay, and there's no recovery here. Okay, and I've seen this with the C++ compiler. Now, it doesn't get lost, but quite often for a relatively simple syntax error, you'll get a dozen error messages, and you really wonder, why did it just go crazy with these error messages? Okay, well, you don't want your parser to get lost. Okay, all right, well, okay, well, here's another strategy. Okay, the parser detects an error and flags it. Okay, and then it recovers by just skipping tokens until it finds something that it recognizes. Okay, so maybe okay, there's a syntax error in the middle of a statement. So then after flagging the error, the parser will then skip over the rest of the statement and says, okay, well, I'm just going to skip the rest of this statement and resume parsing at the beginning of the next statement. Okay, well, that works very well. Okay, and so that's pretty much how we're going to handle syntax errors for the time being. That if there's some error, we'll flag it, and then we will start skipping tokens until we reach a point where the parser again recognizes where it is. Okay, and quite often that just says, well, skip the rest of the statement, and then as you're skipping tokens and you recognize a token that begins a new statement, then resume parsing from there. Okay, and that's not too hard to implement, and pretty much that's pretty effective. Unless you have multiple errors per statement. This will work very well. You'll catch the first error in a statement, and then you resume parsing with the next statement. And so you can catch multiple errors with each during each compile, instead of just stopping after the first error. Okay. All right, so we will implement this very simple error handling. Okay. Okay. Top-down recursive descent parsing. Okay, it's quite a mouthful, but that is very descriptive of the way our parser works. Right, we start with our topmost language construct. Okay, that's program, and then we work our way down. Okay, and you saw that we have lots and lots of these parser member functions: parse program, parse assignment statement, parse expression, etc. Okay, so we start with the topmost construct called program, and then we work our way down recursively. So that's why it's called top-down recursive descent. Okay, so parse methods can call lower-level parse functions. Okay, so for example, there's parse statement. Parse statement calls parse assignment statement. Parse assignment statement calls parse expression. Parse expression can call parse variable. Okay, so you're working your way down. Okay, and then there could be recursion. Okay, so parse statement can be a while statement. A while statement will contain a statement. Okay, and so there's a recursive call there to parse statement. Okay, that's why it's called top-down recursive descent parsing. Okay, now when you write a hand-coded parser, okay, this is the type of parsing you would most likely do. Okay, it's relatively easy to understand and write. Okay, the grammar of the language is encoded in the structure of each of those parser member functions. So for instance, if you look at parse repeat statement, well, the grammar of a repeat statement is encoded in that parser, right? It looks for a statement list, okay, parses statement list. Then it looks for the reserved word until. Then it parses the Boolean expression. So the structure of the parse function reflects the grammar, okay? And there's a very close correspondence between the parser and the parser function and the syntax diagrams, right? If we look at the syntax diagram for a repeat statement, that pretty much tells you how you're supposed to write the parser for the repeat statement, okay? So that's why top-down recursive descent is so popular when it comes to writing parsers, okay? But it does have disadvantages, okay? Can be kind of tedious writing all those parser functions. Error handling is kind of ad hoc, you know, the syntax error handling. And you know, as I said, initially, the easiest thing for us to do is after we've detected and flagged a syntax error, just skip the rest of the statement and resume parsing at the beginning of the next statement. That's, you know, it's kind of ad hoc. And then parse down recursive descent parsers are big and slow, okay? Why are they big? Well, as you've seen, you have to write a parse function for every language construct, okay? And that means at runtime, you're making lots and lots of function calls, okay? And that, you know, function calls are, they're not free. You know, you got to pass parameters, and then you have to return values and so forth. So top-down recursive descent parsers are big and slow, okay? But they're easy to write and easy to understand, okay? Now, if we have top-down, then of course there's bottom-up parsers. Now, they can be smaller and faster, okay? Error handling is still tricky, and we'll talk about bottom-up parsers later on in the semester, and you'll see that, yes, they can be smaller and faster, okay? But they are very hard to debug. So you would not likely try to write one of these by hand. And bottom-up parsers, as you'll learn later, are often generated by programs called parser generators. And parser generator, you know, you feed it the grammar of the language, and it will then generate a parser for that language. And in fact, in a week or so, I will be introducing you to such a parser generator called Antler, and that's what we'll be using in this class. Okay? Now, Antler, it turns out, generates a top-down recursive descent parser. Okay, there are other tools that will generate a bottom-up parser. Okay? All right, any questions? Okay, I know I'm rambling on quite a bit, but if there are any questions, just please speak up. But I thought, yes, did somebody say something? I thought this would be a good time to sort of stop and look at what we've accomplished so far. Okay, so here is that diagram that you've seen many times before. And what have we done? We have the overall structure of our language translator. Here's the overall structure. We got front end, intermediate tier, and back end. Okay, we've got that. Okay. And in intermediate tier, you've seen the rudimentary parse tree. You've seen a rudimentary symbol table. Okay, so we have that. Okay, and by golly, we can actually start executing some of the source code. Okay, now we haven't seen entire Pascal programs yet, but we've seen significant parts of Pascal programs. We have compound statements and assignment statements, statement lists, repeat statement. So that was included in simple. Okay, that first set of code I gave you, and simple can certainly do scanning, recognize tokens. It can do parsing of some of Pascal's statements, and you saw it executing. We were calculating square roots and doing temperature conversions, and so we were able to write some simple programs. And then your assignment number 3, what was to add more statements. Okay, so we made some significant accomplishments already. Basically what we have is a simple scripting engine, right? We can write these little scripts in this, Pascal-like notation, and we can execute those. We can execute expressions, assignment statements. We have control statements, compound statements. We are able to calculate values and store them. Okay, yes, we're using a hack right now, but we can store values of variables. Okay, so we've done quite a bit. Okay, at the very least, I hope everybody has a basic understanding of the components of a compiler or an interpreter, and what the components do. Okay. All right, and remember, this is all about translation, where we're translating the source program, in our case written in Pascal, into, for an interpreter, we're translating the program into the actions. Okay, we're running the program, we're executing it. Okay. All right, and in order to do this, we had to employ some hacks. Okay, so far you've only seen one parse tree and one symbol table. So whenever we parse a source file, we create one parse tree and one symbol table. Later on, you'll see that we'll have multiple parse trees and multiple symbol tables. Okay. All our variables are scalars, right? Where we haven't done records or arrays yet, and then we haven't even declared what the data type of the variables are. We just store whatever value we calculate into the variable. Okay, and that's because we haven't parsed any declarations yet. Okay, and then we have this hack that the first time the parser sees a variable on the left-hand side of an assignment statement, we consider that variable declared, and we create an entry for it in the symbol table. And then subsequent appearances of that variable, we look up that variable in the symbol table. And of course, our big hack is that at runtime, we're storing the values of the variables in their symbol table entries. Okay? So those are temporary hacks. And as we move along, one by one, we will be removing these hacks. Okay? But I want to go ahead and employ these hacks so that we can make forward progress at a very early stage. Okay? All right. Any questions about what we've accomplished? Okay. Now, at this point, I was talking about top-down recursive descent parsing and how that's big and slow. And I can ask the same question about the scanner. Okay? Now, remember how the scanner worked. Okay, it always looked at the current character. If it's a blank, it'll skip the leading blanks until it gets to the first non-blank character. And then that non-blank character told the scanner what type of token it was going to extract next. Is it a word? Is it a number? Is it a special symbol? And if the scanner extracted a word, it checks a table to see if that word is a reserved word. Okay, so the scanner is basically going character by character, extracting tokens. Okay, and again, I would say that our scanner is kind of big and slow. Right? It is creating lots of token objects. It's making lots of function calls while it's doing its job. Okay, so I'm going to show you how we can write a more compact and faster scanner. Okay, but like I said, as I said, with a bottom-up parser, this code is going to be a lot harder to understand and debug. Okay, but I want to show you how we can do this. Okay, all right. Now remember, we were using what I call regular expressions to describe the various Pascal tokens. Okay, so here a Pascal identifier. Okay, it starts out with a letter. Okay, and then it can be followed by any number of letters or digits. Okay, so we will write it out this way as what is known as a regular expression, and this star means 0 or more repetitions. Okay, so the way we read this, again, identifier consists of at least one letter, but then that letter can be followed by 0 or more letters or digits. Okay? All right, that's a regular expression, and then we can use this finite automaton, okay, also known as a state machine, to represent that regular expression. Okay, so this is kind of like, well, it's not exactly the same as a syntax diagram. It's a different way of diagramming here. So these are states. Okay, you can be in state 1, 2, or 3, and this is the beginning state, because this is where the arrow comes in, and this is the ending or the terminal state, and we indicate that by drawing this double circle. Okay, now it's called deterministic. Okay, okay, so here we come in and we're in state 1, and we see a letter. Okay, this because if the next character is a letter, we go to state 2. Okay, and you can see here that as long as we're seeing a letter or a digit, we stay in state 2 until we see some other character, and then we go into state 3, and that's a terminal state. Okay. All right, so why is it deterministic? Okay, it's deterministic because, first of all, the letters that or the characters that we read in determine how we go from one state to another. And here, of course, here we go from state 1 to state 2. And once we're in state 2, as long as we see more letters and digits, we stay in state 2. So that's like a transition to itself. And then if we see some other character, we transition to state 3. Okay, it's deterministic because the next input character uniquely determines which translation to take to the next state. Okay? In other words, here we are in state 1, and if we see a letter that says go to state 2, there isn't, oh, we see a letter, maybe you go to state 2, maybe you go to state 5 or whatever. Okay, none of that. Okay, each input character uniquely determines what transition to make to the next state. Okay, that's the deterministic part of the name. Okay, all right. So this is a little automaton. Okay, deterministic finite automaton, or a DFA. Okay, I know some of you who have done circuit design are very familiar with these state transition diagrams. Okay? All right, so we have the starting state, okay? We have the transition, and we have the accepting state, or the terminal state, okay? It's called accepting because when you get to this stage, at this state, okay, you have accepted the fact that you have just recognized an identifier, okay? So that's why it's called an accepting state, okay? Okay, now we can represent the behavior of a DFA, the behavior being the various transitions, with a state transition matrix, okay? So here, if you're in state 1, okay, and you see a letter, you go to state 2, okay? And if you're in state 2 and you see a letter or a digit, you stay in state 2, okay? But if you see any other character, you go to state 3, okay? So this is an example of a state transition matrix, okay? Has the same information in the table as the diagram, okay? All right. Okay, here's a DFA for Pascal number. It's a little bit more complicated, okay? Okay, we can see that we start out in state 0, and we could see a leading plus sign or a leading minus sign, in which case we go to state 3. Or if we see a digit, okay, while we're in state 0, we go directly to state 4, okay? All right, now when we're in state 4, as long as we're seeing more digits, we stay in state 4, okay? And if we see a decimal point, we go to state 6, okay? But if we see any other character, we go to state 5, which is an accepting state, okay? What if we accept it? Well, the scanner has recognized an integer, okay? Now, if we move out here, and we saw a decimal point, we go to state 6, okay? And after the decimal point, we can have more digits, okay? And so here we spin around in state 7 as long as we see digits, okay? If we see an E, we go to state 9 because we have an exponent. Otherwise, if we're here and the next character is not a digit and it's not an E, we go to state 8, meaning we've just accepted a floating point number with a decimal point, okay? Now, back in state 4, okay, we could have seen an E, okay? So it's possible for a Pascal number to have an exponent without a decimal point. So we come here, and now we're in state 9, okay? Now, state 9 is where we end up if we have an exponent, okay? Well, so we've already seen the E, okay? And the exponent can have a leading plus or minus sign, and otherwise, it's just one digit after another, okay? And then when we finally come to a character that's not a digit, we go to state 12, which is another accepting state. And in state 12, what we have accepted is a real number with an exponent, okay? All right, so we see 3 accepting states here, okay? Now, in this diagram, I only use the uppercase E. If I really, really wanted to be complete, I would have also shown lowercase e. And that means there'd be another arrow with a lowercase e label here. So here and up here. We can either specify both capital E and little e on the same arrow, or we can have a separate arrow for the lowercase e. Okay? But to keep things simpler, I just use the uppercase E for the exponent. Okay? So here's a DFA for a Pascal number. Okay? And of course, I can combine the two. And here's a DFA that will allow a scanner to recognize either an integer or a number. So here I am in state 0. If I see a letter, then okay, it must be an identifier. If I see a plus sign, minus sign, or a digit, then I'm going to end up down here to recognize a number. Okay. So, our diagram's getting a little complicated here. You can imagine if I can add all the special symbols, and this diagram will get even bigger. Okay, so now just keeping the diagram the way it is now. Here is the state transition matrix written as Pascal, or written as a C++ code. Okay, so we're in state 0. If we see a letter, we go to state 1. So here's state 0. If we see a letter, we go to state 1. If we see a digit, we go to state 4. So digit, we go to state 4. Okay. So here along each row represents a particular state. Okay. And each column represents a particular input character. Okay. So state 0, if we see a plus or a minus, we go to state 3. So here, plus or minus go to state 3. If we see a period or a decimal point, well, we can't lead anything with a decimal point, so that's an error. So you see an error entry here. If we see an E, capital E from state 0, well, then we go to state 1. So then we consider E just to be another letter, okay? However, if we're in state 7 and we see an E, then we go to state 9, okay? So you can see that we treat the letter E in 2 different ways, depending on what state we're in, okay? So if you look at this table, the way I've defined it, so it tells you, given what state you're in, that means what row you're in, and the input character, it tells you what state to go to next. Okay, so if you're in state 4, okay, and you see a period, at state 4 you see a period, okay, you go to state 6, okay, which is what the diagram says, okay. Now, the accepting states, 5, 8, and 12, I indicate by making the numbers negative, okay, then. So if I come to a point where I am going to a state where it's negative, then I know that it's an accepting state. Okay? But look at all the error entries, right? I would say that at least half of this table, probably more, is error entries. And if I had included all the special symbols, okay, then this diagram, this DFA, would have been much more complicated, and this table would have been much larger, and I would then venture that more than half of the entries would be error entries, okay? Basically, if you land in an error cell, that means there's something wrong with that token. Okay, it was the syntax error there. Okay, all right. So we have this table. Okay, and using this table, I can write a very, very fast scanner. Okay, in other words, a scanner that will recognize identifiers and numbers very, very quickly, much faster than the scanner we had written earlier up to this point. Okay, so all right, so I pointed out that the negative numbers represent the accepting states, and the letter E, capital E, is handled two different ways depending on what state you're currently in. Okay, and you always start with state 0 according to this table. Okay. All right, so let us write a simple deterministic finite automaton scanner. Okay. All right, so let's see how that works. Okay, so I have a scan function that says, okay, now go and scan the source file. I define some character classes here. Okay, the letters and digits, plus and minus, a dot, capital E, and any other character. And I'm going to define an error state, okay, which I'm just going to make it a very, very negative number. Okay. All right. So that is the error state. Okay. All right. So let's move forward. Okay, just a second here. All right. So okay. I will have my state transition matrix, and the one that I have here is 13 rows by 7 columns. Okay, so here it is, 13 by 7, and I will keep track of what is the current character, the one that I just read in, and what is the current state. Okay? And then the rest is just things I need to read in the source file, I keep track of the line number, what position I am in each line, and so forth. Okay. There's a next token function that says, okay, give me the next token. Whoops, sorry. There's a type of, okay, so given a character, what type of character is it? And you saw earlier that it could be a letter, digit, etc. Okay, so it basically returns one of these values to tell you what type of character it is, and then a function that returns the next character. Okay, so these are the member functions of my simple DFA scanner. Okay. All right, well, let's see how it's going to work. Okay. Here's type of. Okay, so given the character, I determine what type of character it is. Okay. All right, here I'm asking for the next token. Okay, now remember that in the old scanner that we wrote, when we asked for the next token, the scanner looked at the first character of the token, and that told it, okay, what type of token is coming next. Okay, let's see how this one works. Okay, all right, well, just like the other scanner, we skip over any leading blanks. Okay. Okay, we check to see make sure that we haven't messed up reading the input file. Okay, all right, we start in state 0. Okay, that's how we start when we're going to scan for an identifier or a number. Okay, buffer will contain the characters of the token. Okay. All right, so, and of course, that's what we return. Okay, so next token will return the string containing the next token. Okay. All right, so here we go. Okay. We have this loop here. Okay. And we keep on looping as long as the current state is greater than or equal to 0. Okay. Now remember that accepting states are negative. Okay. So that tells our loop to stop. And also error states are that very, very large negative number. Okay? So this loop keeps going as long as the current state stays greater than 0. Okay? Greater than or equal to 0. Okay. Now this statement here in red is the transition. So the new state is the current state that's what row we're in our table. And the column is what type of character we have. Okay, was it a digit? Was it a letter? Was it a dot? Okay, and that the value in that matrix in that row and column gives us the next state. Okay, so this is the state transition. Okay, and that one line is the heart of the scanner. Okay, we'll just keep making state transitions until we come to a state that is negative. Okay? And as we're looping, we're going to keep appending characters to our buffer, okay, so that we can keep track of so we're building the string that makes up that token. And of course, we have to get the next character. Okay, right? So that's how we get the next token. Okay. You can see that a table-driven scanner, again, and this uses that matrix that I showed you earlier, can be very fast. Okay, because as we're consuming characters, we're doing these state transitions. Okay, and this is just one line of code that does all that, this transition. Once we have the next character and we know what state we're in, we can get to the next state. Okay. All right, so here is the scan function. Okay, we go ahead and start off with the current character, and we just ask for the next token. Okay, and that's the function you just saw. That gets us the token string. Okay, and we check, well, what state did we end up in? Okay, if it was -2, then the token we had just recognized was an identifier. If it was -5, the token we just recognized is an integer. Okay, if -8, it was a real number that only had a fraction, and it was -12, it was a real number that had an exponent. Okay, otherwise, we must have hit an error state. Okay, so that's the scan function. Okay. Now, let me do a little demo. Okay, you can see that the scanner is very compact. Okay, now, yes, we're only recognizing numbers and identifiers. Okay, okay, let's take a look at how this guy can work. Okay, so here is our scanner.h. Okay, so here are the character classes. There's a scan function. There's the error state. There's our matrix and the current character, the one we just read in, and the current state. Okay, and then there's next token, which extracts the next token and returns a string. And then this is the type of function that, given a character, returns what character was. Okay, so there's the header or the class simple DFA scanner. Okay, here's the code. Okay, let's see. Okay, there's our matrix. Okay, and let's see. There's next token. Okay, we skip blanks, and then there is that magic line that does those oops, sorry, not that line. This line that does all the state transitions. Okay, here's scan, which then after we've extracted a token, we determine what token it is. Okay, and here's the type of that figures out, given a character, what type of character it was. Here's next char, which then just reads the next character from the input. Okay, and here's the main. Okay, so we're going to scan this particular text file. Okay, so hard code it here in this example. Let's take a look at that text file. Okay, so it's just a file full of various tokens. Okay, and there are some deliberate errors in here. So let's run this thing and see what we get. Okay, lots of room here, and we're going to hang on here. Whoops. Oh, spinning beach ball. All right, I think I could just run it from here. Oh, there we go. So you can see that, okay, here's the first input line, and we recognize hello and world as identifiers. We got a number there, so we recognized it as an integer. Okay, well, we recognized those two words as identifiers. Okay, here is a line containing a real number, and yes, sure enough, we recognize it as a real number that has only a fraction. And then here we have numbers that have exponents, and we just call them real. Okay, I suppose I should have written real with exponent. Okay, and oh, here's an interesting one. This was recognized to be a real number. Okay, and then this running up against it was recognized to be an integer. Okay, so our little scanner was smart enough to do that. And then here we have some numbers with errors in them. Okay, and so, okay, we recognize this to be a real number, but we can't start something with a period. And so the period was recognized to be an error. And then we picked up the 6 as an integer. The 123, well, the 123 decimal point in Pascal, you have to have at least one digit after a decimal point. And so if you look at our state transition diagrams, you'll see that after a decimal point, you have to have at least one digit. So this was recognized as an error, and so forth. Okay, and at the very bottom here, we see a good 1, 2, 3. That should have been recognized as an identifier, and there it is. And then we got an integer followed by another identifier, and that's what we have here. So this is a table-driven scanner, very fast, okay? But you can see that even with just identifiers and numbers, that table was kind of daunting, right? Where is our table? There, okay. And if we had included all the special symbols, this table would have gotten much larger. Okay, this is not the sort of thing you want to do by hand. Okay, now we are very careful. Okay, we drew the diagram, and we are very, very careful constructing this table. Okay, so if we have a lot of tokens, you do not want to try to create this table by hand. And so that's where you run these parser and scanner generators, and they will build the tables for you. Okay, so you want a computer program, right, to actually build this table. And the way it works is that you feed it the definitions of all the tokens using those regular expressions that I showed you earlier. And the utility program will read in all these token definitions, and internally it will then construct the state transition diagrams, and then it will then construct the state transition matrix. Okay. So when we look at our tool, Antler, that we're going to use later, that's exactly what Antler is going to do when it builds the scanner. It will build this very, very fast table-driven scanner. Okay. Okay, any questions? Okay. So you can see that by applying some, circuit logic or computer science or whatever, it is possible to build a very fast table-driven scanner. Now later on, when we look at this bottom-up parser, which I told you was also very fast, it is a table-driven parser. And it's very fast, very compact, impossible to build by hand. Okay, so all right. Any questions? I just wanted you to see this, that it is possible to do this sort of thing, but not by hand. Okay. All right, let me get back to my slide. My cat is sitting on my mouse pad. Not good for mousing. Let me get back to, I think we're just about at the end. Yes, that was the end. Okay. Any questions? Okay. All right. If you run into any difficulties with the current assignment, I know it's not an easy assignment. Please use the discussion webpage in Canvas. Okay. And I will have my regular office hour at 4:30. Okay. So, any questions? Okay. If none, then we will come back on Thursday and make more progress. Okay. All right. No questions, then I will go ahead and stop sharing and end the meeting. Thank you for coming.
Thank you, Professor.
Oh, you're welcome. You're welcome, everybody.